Oh, we're doing the worksheet first. Okay, I need you not to be chatting at this point. Okay, so we're on the packet that says 2.1. Guys, Bryce, please. 2.1, inductive reasoning and conjecture. After this lesson, you should be able to make conjectures based on inductive reasoning, which I need to explain to you what that is. You will also find counterexamples and represent patterns with various math symbols. We're going to apply our geometric terms, etc. So here's your first thing to fill in on your packet. A conjecture is an unproven statement that is based on observations. So, for example, if you see something happening, you might assume something based on what you see. It looks like you're seeing a pattern. You use inductive reasoning when you find a pattern in specific cases and then write a conjecture for a general case. A conjecture may or may not be true. So we're going to write a conjecture about the next number in this sequence. You are going to look for a pattern between the numbers 1, 3, 9, 27, and 81. And we're going to think about what the next term might be and how to get it. So if each number you notice, maybe you've noticed that each number is a power of 3. So there might be multiplying, there might be adding, there might be powers. So we're trying to determine how this list of numbers is generated. 3 to the 0 is 1. Maybe you remember back from Algebra 1 that any power of anything raised to the 0 power is 1. 3 to the first is 3, 3 to the second is 9, 3 to the third is 27, 3 to the fourth is 81. So the next one's going to be 3 to the fifth power. Let's find out what that is. So I'm going to show you how to push that on the calculator. We have some different operating systems in the room. So I'll explain what yours might look like. On the newer operating systems, which are the color graphers, which I'm hoping to get a whole classroom set. I wish I'd find Calc 23. That would get it to me faster. I push 3. I hit this button underneath clear. There's an arrow. Please look on the calculator now. Otherwise, you may not know how to type this in. You should be practicing this, so I should see everybody with a calculator. You go arrow up, and then you put in the power of 5. Okay, then you hit enter. So you need to know where the buttons are, that's all. It's not that big a deal, it's just a matter of knowing how to type it in. Now some of the calculators might look like I'm about to write in a second. I'll show you. When you push the buttons on the calculators that you are borrowing from me, and you hit that arrow up key, it's going to look like something like that. And then you're going to put in 5, and then it's going to say 243. Okay, so the next number would have been 243. When you keep doing powers of numbers, they get really big, really fast. Because what does that mean? It means 3 times 3 times 3 times 3 times 3. Okay, we're going to write a conjecture about the number of small squares in the figure, in the next figure. The sides of the squares have measures of 1 by 1, and this is 1 square. This one is a 2 by 2, and there are 4 squares. This is a 3 by 3, and there are 9 squares. So the next one's going to be a 4 by 4. Okay, and so it's going to have 16 squares. Another way to describe the pattern of numbers would be the perfect square numbers. That's where they come from, by the way. The numbers we call the perfect squares. They are squares with sides that are equal. That's how many squares are in them. Write a conjecture that describes the pattern for each sequence, then use your conjecture to find the next item in the sequence. Okay, we're going to look at this, and we see a -5, then a 10. And then it goes from a positive to a negative, and it's doubled. And then it goes from a positive to a negative, and it's doubled. So what are we multiplying by? Great. Yes, multiply by -2. Okay, so the next one would be 40 times -2, and that is -80. Sometimes we can see what's happening and we know what to write, but we don't know how to describe it mathematically. A lot of you can get this next blank, but you may not know how to describe it. What'd you say? All right, multiply by 10. Did anybody think about another way to say this? You're multiplying by 10 to get the next term. Okay, now there's another way to describe that. Powers. Oh, no, I don't want to write add a 0. I get that. That's what I was thinking we might write if we're thinking in our head. Add a 0 on to the next previous number. But that's what multiplying by 10 does. So we want to try to say multiply by 10 or powers of 10. 10 to the 0 would be 1, 10 to the first is 10, 10 to the second is 100, 10 to the third is 1,000, etc. Okay, this one's harder. So I'm going to give you a hint. 1 can be written as fifths, 5 over 5. Okay, and I don't want you to write add 1 to the numerator. Kenny, did you say something? Excellent. Okay. Add 1/5 to the previous term to get the next term. Okay, adding a fifth. So here's what he's saying. 5/5 plus 1/5 is equal to 6/5. And if you add 1/5 to 6/5, you get 7/5. So that was the pattern. So the next one is, 9/5. A lot of kids aren't real comfortable with fractions, and so they tend to not want to say that. If you were thinking this, good for you. Write a conjecture. All right, angle 1 and angle 2 form a right angle. Now we're going to do some geometric stuff. Angle 1 and angle 2 form a right angle. So what would be true about them? Oh, good. Okay, angle 1 and angle 2 are complementary. Oh, good. Complementary and adjacent. Another thing you could say, someone will come up with something else, because they're not always just one right answer for these kind of questions. Okay, yep, the measure of angle 1 plus the measure of angle 2 is 90. Okay, if that happens again, you're going to turn it into me, Nathan. Angle ABC and angle DB are vertical angles. It's not time to check it either. Oh, did you? Thank you. Okay, so let's say this is ABC. And then where would D be? Up here maybe, and DBE? Okay, these are vertical. I just drew a picture of it just to remind you. What do we know about vertical angles? I'm sorry? Oh, they're across from each other, yep. Or they are equal in measure, so the measure of angle ABC is equal to the measure of angle DBE. Now, someone else might have written that angle ABC is congruent to angle DBE. These are all good things. Anybody still need this page? Okay. No problem. Okay? Write a conjecture again. Now, angle E and angle F are right angles. What would be kind of the most obvious thing to maybe say? They all equal? They equal 90. Okay, so the measure of angle E and the measure of angle F equal 90 degrees. There's another thing we could say, if anybody maybe thought of it, if they're both 90, they are supplementary. Okay, angle E and angle F are supplementary. Let's abbreviate supplementary. No, they're supplementary because they're each 90. The total would be 180. You with me? Okay, I get it. No, I get it because you were thinking right angle adds up. Yeah. Complementary would be two angles that add up to 90, not that are each 90. All right, so now I think you have to flip your page. This is one of the harder things, so please be really trying to focus on what I'm trying to tell you a counterexample is. Some of you might just get it right away. But often when I'm asking this, I find that students forget what I'm trying to get you to tell me. To show that a conjecture is true, you must show that it is true for all cases. To show that a conjecture is false, you must find one counterexample. All it takes is one to make it not be true. A counterexample, this is the word I'm telling you, I find students not knowing what I'm asking in the future, is a specific case for which the conjecture is false. A counterexample must satisfy the if, but show the then to be false. Now I'll explain what that means. I can say something very obvious for you to understand, hopefully, what I'm saying. If it's a dog, I'll do a frog. If it's a frog, then it is green. To give me a counterexample, you have to show me something that is a frog, but isn't green. That's it. So if this is a false statement, right? And the way a counterexample would be a red frog. You know what I know there are some poisonous red frogs out there. Okay? Pardon? Some are not even poisonous or red. I just made something up, though. It doesn't have to be red either. It just has to be not green, okay? So what I'm trying to say, so what the point was, the part about the if, the part after an if, that has to be true. The part after then has to be false for it to be a counterexample. So we're going to show, I want you to see a counterexample. This is already solved for you, and I want to explain it. If segment AB is congruent to segment BC, then B is the midpoint of AC. Okay, so what you are thinking is, can I draw something where AB is congruent to BC, but B is not the midpoint? So AB and BC here are the same length, agreed? They're 003. But B is not the midpoint of segment A to C. It's not even on segment AC. B is not even on it. All right, so they don't have to be collinear. So the question you have to ask yourself is it possible to draw a diagram so that AB is equal to BC, congruent, such that B is not the midpoint? And the diagram here is a counterexample because B is not the midpoint of the segment A to C. So that makes the conjecture false. So now we're going to try some more together. First, we're going to determine whether it's true or false. Well, actually, we're going to try to figure out if it's true or false. And then if we can, we're going to give a counterexample if we believe it's false. Okay, if points A, B, and C are collinear, that means they are all in one line. Okay, so we know we're going to have 3 points in a line. Then AB plus BC equals AC. If we do this, then B would have to be between the A and the C to make this true. Okay? Do we have to put points A, B, and C with B in between the A and the C just to make them collinear? Can we draw it so that B is not between there? So you could do A, then C, then B. And now that's not true over here. Are you with me? I just made this part be true, but this part be false. So this would be a counter example. This statement was false. I can make a counterexample that shows that it's false. Okay, the next one. If angle R and angle S are supplementary. Okay, so I'm going to make an angle R. I'm going to say that it's 120. And then I'm going to make an angle S so that they're supplementary, which would make angle S have to be 60. So right now I have done the if part. And I also need angle R and T to be supplementary. So I need to make an angle T that would be supplementary with the angle R. If angle T is going to be supplementary to the angle R, it would also have to be 60. Okay. So now the then part says, then angle T and angle S are congruent. When we wrote down what it said in the beginning and made sure that this is true, does the last part have to be true? Does angle T and S have to be congruent? And the answer is yes, they do. So this statement was true. Okay, we don't have a counterexample. All right, that statement, do you see how I cannot even make this statement be false because of what the beginning part said? All right, let's try another. Just takes a little bit of practice to starting to see what you're trying to do. All right, I've got angle ABC and DEF supplementary. So I'm going to draw something that makes this true. Supplementary angles. Oh, wait a minute. It says I have to draw it so that they form a linear pair. Do I have to do that? No, this is false. This is false because I can have two angles be supplementary. I can make an angle ABC. And say I said that's 110. And then I made an angle DEF. And I said that one is 70. Well, those are supplementary, but they don't have to form a linear pair. So this would be the counterexample. I could have also just been two 90s that weren't attached also. That's another way to have done it. They didn't have to be congruent though. You don't have to draw this. I just thought I'd point out it wouldn't be wrong for you to do this. Okay, about number 10. I have to draw segment DE perpendicular to EF. All right, so I'm going to make a segment DE. And then I'm going to make a segment EF so that they make a right angle, because that's what that perpendicular means. You need to know the vocab. Okay, so I made the if be true by drawing this picture. Now I'm going to see, is the then true? Is angle DEF a right angle? D to E to F? Yes, it has to be. So this whole statement was a true statement. Any questions about 10? How I knew to make... You got your pass right. Alrighty. Okay, next one, same ideas. If angle ABC and CBD form a linear pair, so I need to make a linear pair. I need an angle A, B, C, and C, B, D. Now I just made myself a linear pair. Oh, wait a minute. The then part says they have to be equal measures. Well, that's false. Because I just drew a linear pair where they aren't equal angles. One's bigger than the other. So they were implying they would have to both be 90, and that's not true. And this would be my counterexample. They're not congruent angles. You do not have to write counterexample. I'm just writing it because I'm teaching it. Okay, you don't have to write counterexample down. You just give me this picture, and I know you know what you're talking about. Okay? Draw me something that makes it false. Well, this one's tricky, but each of my classes, second and fourth today, have figured out what it needs to be in order to make the if part true. I gotta have, look out, you see the B in both of these? That means those are connected, doesn't it? And the C, wait a minute, and that, and the A, and that it means they have to be connected. It says that we want to have AB, BC, and AC congruent. So if I make a segment, AB, and I want it to be congruent to another segment that has B in it, but also has as a BC, and then I want the segment from A to C to be congruent. Yay! You got it. I'd have to make a triangle because I'd have to have C be the same length, B to C, sorry, and A to C to be the same length. I have to make a triangle with all its sides equal. So are they collinear? They can't be collinear. And that's what we would get. I mean, how could you do that? If they were collinear, they're saying this. A to B is equal to B to C, and A to C is equal to that. No, it's twice. You can't do it. Can't make that. It's impossible. All right. I think we're getting close to being done. If AB plus BC equals AC. All right. I'm going to make something that makes this true. B is going to have to be in between A and C to make this a true statement. So this part's got to be true, so I'll just put B somewhere. Remember, it doesn't have to be right smack in the middle. Oh, then does AB have to equal BC? Did I have to put it in the middle? And the answer is no, this was false, and I just made myself a counterexample. This is a counterexample. No, I don't have to write the word counterexample. Okay, the next part is the assignment, but before we do that, we're going to quick fill in the ISN, and it's really short. It's just on the front cover's back of the front cover. A conjecture is an unproven statement that's based on observations. Write a conjecture from this statement. Angle ABC is a right angle. The conjecture would be the measure of angle ABC equals 91. Can't be 91. It says it's a right angle. If angle ABC is a right angle, you can conclude that the measure of it is 90. It has to be. No, not counter. This one's just make a conjecture. So if we are told you have a right angle, then it measures 90. Okay, that's it. That's a conjecture. Then now we got that confused with counterexamples. So we want to make sure we get the difference. So to show that a conjecture is true, you must show it's true for all cases or prove it. To show that a conjecture is false, you must provide one counterexample. A counterexample is, again, a specific case for which the conjecture is false. All you're doing is showing it doesn't work for all cases. So we're going to prove this statement false. If two angles are supplementary, then they make a linear pair. We already did this one. We said two angles could be non-adjacent. If this is 120, then the other one might have been, well, would have to have been 60, but they don't have to be a linear pair. All right, so this conjecture is false, and this is your counter example. And Evan, if you don't feel like writing the word counter example, it'll be okay. I think I provided us with a second opportunity to give an example. So I wrote an example number 2. If angle DGM is obtuse, that means it's over 90, then angle DGM has to be 120. Well, false. Can I make a different angle that's obtuse? How big could it be? So you just make one that's not 120. So mine's I don't know, that's about, maybe 145, sure. 140, I'll just say 140. Just make it easy. I don't care what you guys wrote. Could be anything between 0 and 90, just as long as it's not 120. 90, oh, not 0, 90 and 180. Okay, so the only other thing you might, well, that's enough for that. I might state it another day. All right, so I'm going to let you have your